best student paper. So. All right. So I'm here to talk about classification and about multilabel classification in particular. And then we introduce how to say combine this instant-based learning and logistic regression together to solve the multilabel learning problem. And for the people who doesn't know who's who, this is me. And I can say so basically we are typical PhD student and professor. Right. Okay, so multilabel classification is everybody goes to Flickr and then you know this tagging system like Flickr. So basically you saw the picture and you give different labels to the picture. So for one single picture, it can at the same time have different labels. Like for example, this picture it can at the same time belongs to sky, house, the grass, and so on. And in social bookmaking, like for example, delicious, and for one particular website, like for example Twitter, at the same time it can belong to Web 2.0, social, community, blog, and so on. And actually, I think Robert just talked about this similarity website, which is also kind of a tagging system. It's also a multilabel system. And another example is, for example, Google Mail. And everybody using Google Mail here. And in the Google Mail, we also have this multilabel system, which from a finite set of labels, then you assign one single particular emails a different type of labels at the same time. So formally that, compare with this conventional classification is, in multilabel classification, instead of assigning an instance one single label, we, in the same time, we assign a set of labels to one instance. So this is the basic difference between the multilabel system and the conventional label classification problem. And you may already feel that this kind of multilabel learning problem is really an important and popular problem, both in practice and also in theoretical aspect. So there are already a lot of, quite a number of work on this multilabel learning problem, and most of them are model-based approach. So the idea is that I give you a training data, then you train a global model, and in the test time, you just apply this model, they give you the outcome, right? And, but on the other hand, if you think about it, this instant-based approach is so far not, intensively addressed it. This is somehow strange because we know that in this conventional classification, in binary classification, this nearest neighbor instant-based approach is very strong, right? But in multilabel case, it's not yet, fully addressed it. So one exception is maybe this MLKNN approach. MLKNN is an instant-based approach for multilabel classification, which is first proposed by Zhang and Zhou in 2007 at the recommendation. And this approach, instant-based approach, has shown very, very strong performance. Compared with a state-of-art model-based approach like Rapid and Adaptos, is underperformance in a lot of data sets. Okay, so there's two things here. First, it shows the potential of instant-based approach for multilabel classification. And the second is, even though that MLKNN shows very good performance, but we still believe that the potential of instant-based approach is not fully exploited yet. And one major reason is it doesn't consider the correlation of labels, right? And actually, we believe that in multilabel setting, the correlation of labels is very important. For example, one paper which is belong to computer science is more likely also, have to label mathematics rather than enrollment. But this kind of label correlation is crucial for multilabel classification, which, by the way, is ignored by this MLKNN approach. So in this work, we believe the following contributions. We propose a new multilabel learning approach. And this approach combines nearest neighbor principle, combines instant learning and logistic regression together. So in a sense, we blur the distinction between the model-based and instance-based approach. And we take the correlation between labels into consideration. Right? So let's talk about the approach. The key idea is we consider the labels of labels as an extra features of an instance. For example, you have a data set here, and here, for example, this is the test instance, and these three are the nearest neighbors of this test instance. And now the question is, does this guy, this test instance, like basketball? To answer this question, we consider the label information in the neighborhood as an extra feature. For example, we have one artificial column here. Like here, for example, means that among the labels, the three labels, two of them like basketball. All right? This is our extra feature. So this is the key idea. And now let's work on this mathematics stuff. So let's consider a test instance, say x0, and let's define a distance between different instances. So this xi is one example from the training data, which we know the label, right? And then the posteriori probability that this test instance has a positive label is given by this, right? Giving the label information of the training data and what is the probability that this label is positive. Let's, for now, let's just consider binary case, okay? Before we jump into which label case, we just first consider binary case. So we have these two things, and then just by apply, we look at this ratio, we just apply the base inputs. We immediately end up with this formula, right? So here the first part is the likelihood ratio, right? And the second part is just plot. Base inference. Directly we just come up with this. And just for the sake of simplicity, we denote this likelihood ratio with rho. All right? Okay, so then I take logarithm on both sides, then we just immediately come up to this. So this is the likelihood ratio, then plus some prior term here. Again, for simplicity, I denote this prior term using omega zero. Okay? So here's the idea. As I said, we want to use instant-based approach. So basically, we want to apply this nearest neighbor principle. If you want to apply this principle, which means that this likelihood ratio rho should be a function of this distance r. And the idea is, if there's a guy which is very close to me, has a positive label, and make me more likely to be also positive. This is the reasoning behind it. And there are different ways you can model this rho. And in particular, we define this in this way. You can define another way, but this is one particular way to do it. So here, so alpha is just a parameter. You can consider now it's a constant. So let's see how this rho behavior. We have different situations. One is delta is go to infinity. Let's say if there's a guy which is very far away from me, so no matter it is positive or negative instance, it should not have any influence on me because it's very far away from me. And if this instance is very close to me, then when it is a positive example, the rho goes up, which means make the positive instance for me more likely. Otherwise, rho goes down, which means that it makes me less likely to be a positive instance. Okay, so this is the dynamic of this function.